So in 6.1, we make a transition from discrete distributions to continuous distributions. So if you remember back in module 5, we were talking about discrete distributions. And this is an example of a discrete distribution. So if you were to roll a 10-sided dice, the outcomes are discrete. You can only roll a 1 or a 2 or a 3. You cannot roll a 2.55 or a 3.14 on a 10-sided dice. So for a 10-sided dice, there are 10 discrete outcomes. And if we wanted to look at the probability distribution, assuming that it's a fair dice, it may look something like this. So notice the outcomes are listed on the x-axis. So here are the outcomes, the dice roll that you make. And then the probability of each dice roll would be 10%. Now, there's a very interesting relationship between these two numbers. If you have 10 outcomes, or in other words, the width of this base is 10 units, 10 units wide, then that means that the height has to be 1 over 10. 1 over 10 is 0.1, which is 10%. And so it's very interesting, this relationship. And if you multiply these two numbers and you were to add up the area of all of these rectangles, you would get an area equal to 1, or an area of 100%. You could think about it that way. Remember, we're going to be sort of transitioning back and forth between decimal notation and percent notation. So make sure that you're, 1 over 10 is 0.10, which is 10%. So make sure that you can do that rather quickly sort of in your head. But this sets up a transition into continuous distribution. So instead of looking at dice rolls where you have discrete outcomes, let's look at another situation that is continuous. This situation is the wait time probability. So let's say you're in the big city and the subway arrives every 10 minutes. You arrive to the subway platform. How long do you have to wait until the subway arrives? Well, you could be waiting 2 minutes, you could be waiting 8 minutes, or you could be waiting 3.14 minutes. This is a continuous situation because you can acquire any number from 0 to 10, smooth and continuous, right? It's not just the discrete numbers of 1, 2, 3, but it's the infinitely many possibilities in between those two. Time is a continuous measurement. Time is continuous. And so once again, you'll notice if we're waiting on the subway platform, we have a base equal to, in this case, 10 minutes. That's the base of our rectangle. And therefore, each probability is 1 over 10. So notice the 10 here, 10 minutes, and 1 over 10. So there's a reciprocal relationship between the base and the height of the rectangle. And once again, if we were to calculate the area of all of the probabilities, this area would equal 1, or 100%. So if you added up all of the outcomes, you'd get 100%, right? Just like if we added up all of the outcomes here, we would get 100%. So this is a good transition into continuous probability, going from a discrete probability to a continuous probability. And here is basically a summary of what we just talked about. And so the total area of the histogram is 100%, or 1. And there is a relationship that exists between the base and the height of the rectangle. So if you have an interval of 10 units, the probability of the height is 1 over 10. If it's 6 units, it's 1 over 6. If it's n units wide, then that means it's 1 over n units tall. Okay, so we apply this. Here again is that subway distribution that we talked about. So you're waiting for the subway and it arrives every 10 minutes. So some people have a wait time of 0 minutes. They arrive on the platform and the doors are open and they walk right into the subway. Other people arrive at the subway platform and it is just pulling out of the station and they have to wait the full 10 minutes and every other time in between. So now we can start asking some questions about these situations. For example, what is the probability, let's go to this one, between waiting 0 and 3 minutes? So what is this probability? And what you're going to find is that this word probability is the same as area. So if we go back up here, we would like to know what is the probability of waiting between 0 and 3 minutes. What is that probability? What that's really asking is, what is the area of this rectangle? What is this area? If you can find the area of this rectangle, that is the same as the probability of waiting 0 to 3 minutes. And so we know a formula for areas of rectangles. We know that area is length times width, or some people call it base times height, right? You basically multiply a number on the x-axis by a number in your y-axis, right? So that's the idea. So I'm a little preferential to base times height. So that's what we'll call it. We'll say the area is base times height. So what is our base? Our base for this rectangle is 3. What is our height? 1 over 10. And so the probability of waiting is 3/10, which is 0.30, which is 30%. So there is a 30% chance that someone arriving on the subway platform will have to wait between 0 and 3 minutes. And we calculated that probability by finding an area of a shape, of a rectangle in this particular case, okay? And now we can ask all other sorts of questions about this, right? What's the probability of waiting between 3 minutes and 6 minutes? Well, you'd find the area of that rectangle, or between 4 minutes and 9 minutes. What would be the probability of waiting more than 3 minutes? More than 3 minutes. So what would be that probability? Well, we could make a rectangle out of this. And there's actually 2 ways that we could find this area. One way would be to calculate it directly. So you could take this and you could say, well, my distance from 3 to 10, so 10 minus 3, that's equal to 7. That's my base. And then I would take 7 and multiply it by my height, 1/10, to get 7/10, which is 70%, right? Or 0.7. So that would be the probability of waiting more than 3 minutes, between 3 and 10 minutes, okay? Another way you could find it is by using the complement. If you know that the red area is 30% and you know the entire area is 100%, you could use the complement to quickly deduce that the green area is 70% because they're complements, right? They have to add up to 100%. And so there's all sorts of little tricks that you can use, like using the complement, using just kind of a composition of shapes, subtracting shapes or adding shapes together in order to find out all of these different areas. But the bottom line is that when they ask you for a probability, you're actually finding an area. And in this section, the areas that we're looking for are rectangles. So here is our rectangle, zip, zip, zip. And we have one point that's at 2, one point that's at 7. Now, I know that it's at 2 and 7, so there's a couple things that I immediately know. I know that my width, my base, is 5, and I know that my height is 1 over 5. Remember that reciprocal relationship that we talked about earlier. We'd immediately know the base, and we immediately know the height. And they're asking us to find the area, the probability between 3 and 4. So they would like us to find the area, the probability of that rectangle. And so I know that area is base times height, and the base is 1. The height is 1/5. So 1 times 1/5 is 1/5. 1/5 as a decimal is 0.2, and 0.2 as a percent is 20%. So this particular distribution, it's uniformly distributed, it's continuous, and the probability is 0.20. The time it takes me to wash dishes, well, actually, I use a dishwasher, but if I were to wash dishes by hand, it'd be between 7 minutes and 14 minutes. Okay, so that's my minimum and my maximum. What is the probability that washing dishes tonight will take me between 8 and 9 minutes? And so 8 is this number, 9 is this number, not drawn to scale. Maybe I should draw this a little bit better so it looks. Let's put the 8 here. There we go. There's the 8, there's the 9. Here is my rectangle, just like that. And now I got to find this area. So the area is going to be base times height. My base is 1. My height is 1/7. So the area or the probability that it's going to take me 8 to 9 minutes to wash the dishes tonight is 1/7. So that's going to be 0.14. So there is a 14% chance that it will take me between 8 and 9 minutes to wash the dishes tonight. The time it takes Lizzie to eat an apple is uniformly distributed between 5 and 12 minutes. So I'm going to put a 5 here. I'm going to put a 12 here. Once again, just from those two numbers, I know my base is 7, right? 12 minus 5 is 7. And I know that my height is 1/7. What type of distribution is this? Well, they tell us it's uniformly distributed. So I know that it is a uniform distribution. So I'm going to select the U, the letter U for uniform. This is going to go from 5 to 12. And now questions B, C, D, and E are going to ask you specific questions about this distribution. So what is the probability that it takes Lizzie less than 4 minutes? So if we put a 4 here, what is the probability that it's less than 4? 0. Our minimum value from the given information is a minimum of 5. The probability that it takes her less than 4 is 0. It's outside of our box. There's no data there. So this is 0. That probability would be 0. It's outside of our drawing here, okay? So that's part A. Part B, what's the probability that it takes Lizzie at least 6.3 minutes to finish the apple? At least 6.3. So at least means more than 6.3. So I need to put a mark at 6.3, kind of like this. And we're going to shade this whole entire area. I need to know, what is this area? What is that area? Greater than 6.3, at least 6.3. So I know that area is base times height. I know that my base from 6.3 to 12 is going to be 5.7. That's the distance from 6.3 all the way up to 12. That's 5.7. And the height is 1/7. So I'm going to go to my calculator and I'm going to say 5.7 divided by 7. And that is the area. This area is 0.8143 or 81.43%. There's an 81.43% chance that Lizzie will take at least 6.3 minutes to eat the next apple. So we're going to put this in here as a decimal, 0.8143. Let's look at problem D. Okay, so this was C. So let's get rid of this. Zip. We'll erase this stuff and we'll erase this point. There we go. Okay, what is the probability that it takes Lizzie between 5.2 and 10.5? So that means we need a point at 5.2 and another one at 10.5. Zip, zip, zip. And we are going to find this area. What is that area? Area and probability are used interchangeably here. The area is the probability, and the probability is the area. So if you find the area, you find the probability. They're the same thing, right? So the area is base times height. The base, 5.2 up to 10.5. I think that's going to be 5.3. And my height, I know that from the very beginning, 1/7. So if I take 5.3, and I divide it by 7, I get about 75%. So I'm going to copy this number and I'll paste it in here. Boop, there we go. And I'll round it to 4 decimal places. There we go. So 75.71. That is the probability that it'll take Lizzie between 5.2 and 10.5 minutes. The numbers, I mean, I know they're numbers and it's like 7.5 and 7.1, blah, 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 blah. Understand the concept. Understand what we're doing. We're finding areas, which are the same as finding probabilities. This is an important connection you need to make. Area under the curve is the same as probability. Probability is the same as the area under the curve. What is the probability that it takes Lizzie fewer than 5.2? Okay, well, fewer than 5.2 is going to be this region right here, right? And more than 10.5, well, that will be this region up here. In order to find these two green regions, we could find them independently. We could find the area of the green region, we could find the area of the other green region, add them together, and we'd be done. Or we could use the idea of a complement. We already know that the blue region is 0.7571. And so the area of the green region is going to equal 1 minus 0.7571. This is the idea of a complement. And so all we have to do is go to our answer and subtract it from 1, and we will get 2429. That will be the area of the green region, 0.2429. Submit. And they're all green. What we're doing is finding different areas of rectangles. That's all we're doing so far. That's all we're doing. Areas of rectangles. And the important concept that you want to get from this is that probability is associated with area, and area is associated with probability.